So beryllium, boron's electron configuration, we have the 2s2 electrons, and then we start to get into these p electrons. So we have one electron, excuse my poor drawing abilities, in a p orbital. Now it would make sense that it's easier to remove this electron here than it would be to remove one of the paired electrons in an orbital that's full. This one's not paired. It's a third electron that is definitely going to feel repulsion from these two paired electrons, so easier to plunk that off. And so that is what gives us this idea that we actually, well, the reason why we see these little peaks and troughs. We also see a couple more examples of that, where we see the peak between nitrogen and oxygen. So when we take a look at nitrogen, nitrogen's right there, and oxygen is right there. Now if we look at our electron configuration for both, we can quickly do that. Nitrogen has an electron configuration of 1s2, 2s2, 2p. Now there's 7 electrons to worry about, so 2p3. What this tells us is that there is one electron in each of the p orbitals. Again, excuse my poor drawing abilities. Now when it comes time to oxygen, we have 2p4. And what this tells us is that, again, we have electrons in each of the p orbitals, but one of the p orbitals has an extra electron. Now, why is it easier to remove this electron than it would be to remove one of these 3 electrons from nitrogen? We've seen in the case of beryllium that when we have a pairing, it's easier, or it's more difficult to remove an electron from a pair than it would be to remove one electron that's by itself in an energy level. Well, now we need to start looking at the number of electrons we're dealing with. In this case, in the case of nitrogen, we had one electron spread out across 3 orbitals, each orbital in a different plane. Now in the case of oxygen, we have an electron that's paired up. We now have 4 electrons. One of these orbitals is full. And with a full p orbital, that's going to throw off the symmetry of the repulsion between the electrons. So now instead of, this energy being spread evenly over 3 planes, we now have one of the planes that has 2 negative charges in it. And so it would make sense that it's easier to get rid of this extra electron right here and restore the ion, which we would create, to a place where we have 3 charges spread out over 3 planes versus 4 charges spread out over 3 planes, one plane having an imbalance of a charge compared to the other 2. And so when we start to take a look at the different shapes of the periodic table, this starts to make sense as to why the periodic table is designed the way it does. We take quickly a look at the D block electrons. We can see that there's some crazy shapes here. Again, electrons are trying to maximize their spaces away from each other. We have 10 elements across the D block, 5 different types of orbitals. So 2 electrons in each orbital, even though we see we've got these almost like double dumbbell type things going on, but you would put the energy of 1 electron into each half of the orbital, and that's the way the electrons exist. And the math tells us that this is what the orbitals look like. So it may seem counterintuitive, but that's just the way it is. So what you can do right now is what we're going to do is take a look at the energy levels of electrons, because this idea of electron configuration starts to get a little goofy after a while. We know that the 1s electrons are the lowest energy. Then we have 2s's, 2p's, 3s's, 3p's. Now when things get a little goofy is when we start looking at the 4th energy level. Because of the fact that these d electrons, the d orbitals, sorry, there's 5 of them, and they're crammed so much together, even though the electrons are technically in the 3rd energy level, if they're found in the first d block, and that first d block is this block right here. So it's on the 4th energy level, but these guys, the first set of transition metals all in here, their outermost electrons are in their d block electrons are in the 3rd energy level. So it turns out that the 3d orbitals in terms of energy actually come between the 4s and the 4p's. And so when we start to set up our order, it's always 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then our 4p's. Alright, so that's one of the things you're going to have to remember, is that the 3d's actually come in between the 4s and the 4p's. Then we go to 5s, and then of course, would make sense, the 4d's, then the 5p's. And for our purposes in grade 11, that's about as far as we're going to go. We're not going to start getting into the 5Ds, but you can see that, or the 4Fs, but you can see that once we start to get F orbitals, they actually split slightly above the 6 S's. So it will go 6S, 4F, 5D, 6P. But again, for our purposes, we're not going to bother with that in grade 11. So what I would like you to do is, for your homework, I would like you to try out doing the electron configurations for these guys, and they'll definitely be posted online, and I'll have a brief video explaining or going through all of these. One trick that you can do that is done, it's typically done when we start getting into more difficult electron configurations. In the case of boron, say I wanted to be lazy, instead of writing the 1s2, I could make a set of brackets and I could put the closest noble gas to boron. And when we start to get into some of these, into some of the transition metals and the elements we find in the 4th, 5th, and 6th energy level, sometimes it makes sense because your electron configurations will take up half a page. But the first 20 elements, we wouldn't worry about that. I even wouldn't worry about that until I get into the 5th energy level. So if you have something in the 5Ps or the 4Ds or something like that, then I would do that. But anything before that, write it all out. Anyways, try doing these right here for homework. Like I said, the answers will be posted, and I will have a small video lesson going through how to do all these.